For 5.10 and 11, we're talking about optimization. As we mentioned in class, our knowledge, our calculus skills of finding an absolute max or a min already exist. We did that in 5.5 with the candidate test. As a reminder, 5.5, you can go back and look at it if you need to, but we take the derivative and we set the derivative equal to 0 to get our critical points, and so places where the derivative equals 0 or doesn't exist. And then we take those plus any endpoints of a closed interval and we plug them into basically like a t-chart or an organized way to show that we are evaluating the original function at each of the critical points and endpoints. And then once we have all of the possibilities, we say, yeah, this one's the highest, so that must be the absolute max, or this is the lowest, so it must be an absolute min. The difference between 5.5 with the candidate test and 5.10 and 11 is that here we aren't given the function to start with, and so really it's a pre-calc skill of figuring out how to get to that function ahead of time, okay? So we are optimizing. I'm going to go through the quick notes that I already have on here. Hopefully you copied those down from the posted notes, or you can pause it and copy them down now. And then I'll do the check your understanding questions. So optimization is about finding an absolute max or min in an applied setting. Like in our example, we were looking for the minimum cost given a constant volume for our can. So number one, we write our equation for the variable to be optimized. A lot of times this one will come from geometry, and it likely will have more than one variable in it other than the thing we're trying to optimize. So for example, in our can problem, we were trying to minimize cost, so we have a variable for cost, but cost was written in terms of both H and R. We had 2 pi r squared times the cost of the base aluminum plus 2 pi RH times the cost of the sides aluminum, the aluminum that made up the outside of the can, or the sides of the can, sorry. And so that's our first step. And like I said, a lot of times that has more than one variable in it, or the variable that we're trying to optimize, or in this case minimize, is defined in terms of more than one variable. Okay, but the formula comes from, in this case, it was geometry. Geometry shows up a lot. Step number 2 is we use the constraints to find relationships between the variables. Now, you might not remember what constraints are, but the constraint equations are the ones that kind of like back with linear programming that you would have done in Algebra 2, that give us another relationship between our variables. So in this case, we needed another relationship between our radius and our height to be able to replace one of those variables in terms of the other. So we knew that the volume was a constant. I think it was 365.308 or something like that. And so using that and setting that equal to pi r squared h, we were able to solve for h in terms of r, and so we got the 365.3 over 2 pi, or over pi r squared, sorry, to be equal to h, and then we took that and we plugged it back in. That's step number 3. So once we have another relationship between those two variables, in this case height and radius, we plugged it back into the equation from number 1 to get whatever that variable is, in this case cost, in terms of a single variable. And if you don't remember any of this, you can go back and look at the 5.10 and 11 EFFL. It is in Schoology. And if you want to see a completed one, let me know. I can share that. All right, so then at that point, we've done all of the pre-calc stuff. Okay, so steps 1 through 3 are really about pre-calc. Once we get to step number 4, this is now 5.5 stuff. This is the candidate test. So now we're finding our max or min from the candidate test. Now, we could also use a first or second derivative test. Usually with an optimization problem, you don't have a ton of critical points, so there aren't a lot of options. And the example that we did with the can today, when we took our derivative and set it equal to 0, the radius of, it was something like 2.65, that was the only possible critical point. And we can tell that our derivative was changing from negative to positive there, if you remember the first graph. So we can see that that is going to be the minimum without having to say, okay, well, let's check the endpoints, because the endpoints, I mean, mathematically speaking, would be approaching 0 and approaching infinity, which isn't really feasible. All right, so, which I have here, endpoints are usually not feasible in these scenarios. So really, you're not going to have to do quite as much work as you normally do with candidate tests. Okay, so let's look at a couple examples. And fencing, this is a really common one. So we have 200 feet of fencing, linear, and we are enclosing a rectangular field by our house. One side of the field borders a pond and does not require fencing. Okay, so let's look at a picture here. So here's the side, this can be the pond, and then we have a rectangular pen a rectangular field, mostly rectangular, that we are trying to enclose. Okay, so we are looking for the maximum area in here that we can get with our 200 feet of fencing. All right, so let's start there. We want to maximize area equals, so I need some variables. Let's use x and y. You could use length and width, doesn't really matter. So I'm going to do a equals x times y. Okay, so that is step one. That's the equation for my variable to be optimized. My variable to be optimized is a, but it's in terms of both x and y. So now I need a constraint equation. I need another relationship between x and y. And that's where this other part comes in. I have not yet used that 200 feet is my maximum. Well, because it's a rectangle, I know that this side is also y, and I also know the sum of these three sides is limited to 200 feet. So x plus 2y is equal to 200. And this gives me a relationship that I can use for substitution purposes. So that means x is equal to 200 minus 2y, and I can take that and plug it in here. So I now have 200 minus 2y times y. We can stop there. I'm going to go ahead and distribute so I don't have to use the product rule when I take the derivative though. So 200y minus 2y squared. Okay, so now a is equal to this. I'm done with step number 3. I plugged it back in, and now step 4, I'm doing the candidate test. So a prime is equal to 200 minus 4y. Set that equal to 0. I get that y equals 50. Okay, move the 4y over and divide by 4. Y equals 50, and then now, pay attention to the wording of the question. In this case, it doesn't want to know the dimensions. It says, what's the area of the largest field we can enclose? So now I'm going to take that and plug it back into my area function. And again, with candidate tests, I would be testing multiple options, but like our limits are 0 and 200 for the endpoints, and if one side is 0 or one side is 200, the fence doesn't really exist. So, all right, so, or it technically be 100, but again, we don't care about that. So area is equal to 200 times 50 minus 2 times 50 squared, which, kind of running out of room here, is going to be 10,000 minus 2,500 times 2, which is 5,000, which is 5,000, square feet. 5,000 square feet is our maximum area. Okay. Number 2, a rectangle has 2 vertices on the x-axis and 2 vertices on the curve of y equals 9 minus x squared. We're trying to maximize this rectangle, so I'm going to start with a picture again. So 9 minus x squared is a parabola opening downward, looks something like this. So this y-intercept is 9. This is the line y equals 9 minus x squared. Okay, 2 vertices on the x-axis and 2 vertices on the curve. So that means that I'm looking at something like this. So 2 vertices right here and here on the x-axis, and then 2 vertices on the curve. Okay, and so we're trying to maximize the area of that rectangle. So we want to maximize A equals, all right, let's get some dimensions. I do know, since this point we're going to call x, y. If you want to use different variables like a and b, that's fine. So this point is x, y. That means this distance is x. That means this distance is also x. So my dimensions are 2x by a height of y. This one shows up frequently. Be very careful. Make sure you're doing 2x, not just x. So maximize the area. We have 2x times y. But again, not in terms of a single variable, so I need to do some substitution. That's where my other relationship, which is this one, comes into play. This tells me that y is 9 minus x squared, so let's replace the y right here. 2x times 9 minus x squared. And again, I'm going to distribute so I don't have to use the product rule. So 18x minus 2x cubed. Okay, now we're doing the candidate test. Now is the calculus part. All of that was pre-calc. So a prime equals 18 minus 6x squared. Getting my critical point, setting that equal to 0. Let's divide everything by 6. So we get 3 equals x squared. So x equals plus or minus root 3. Now here I do have two different points, two different critical points. So I'm going to need to plug those back into my original area function, which is this one right here, in terms of x, to figure out which one gives me the max. Now, in this case though, I can see because of the symmetry that calling this x or calling this x are going to give me the same rectangle. It's just a matter of whether I go to the left or the right first. But I still have the same rectangle. I'm going to have the same value when I plug it back in. So either of these x values is fine. Okay. All right. So maximum area then is going to be 18 times root 3 minus 2 times root 3 cubed, which will be 18 root 3 minus 6 root 3, which is 12 root 3. You could also have plugged that back into the 2xy or the factored form. Honestly, that would probably be the easiest because I would have 2 times root 3 times 9 minus 3, which is 6, and I get to 12 root 3. I don't have any units, so I don't need any units on my answer. All right, I'm going to do, let's see, I have 3 more, so I'm going to do the last 3 in a separate video.